Well, we have seen last week that the diffusive noise is nice because it can be described stochastic spike arrival. It can describe the noise generated in a network of neurons. Therefore, it looks like an attractive noise model. On the other hand, as just discussed, it's difficult to calculate quantities such as the time-dependent interval distribution. Whereas this is easy for the escape noise model considered this week. So the question arises whether there are systematic methods to go from diffusive noise to an escape noise model. Now this is going to be an approximation. It's not the same noise model. But the question arises, is this a good approximation? So let's see how this could work. As we have seen in this lecture 6.4, for stochastic spike arrival models, we can calculate the deterministic trajectory, and the real trajectory stays nearby and builds up some kind of Gaussian distribution. So if we project at this moment, t, if we project all the membrane potentials out there, we would find a Gaussian distribution, a nearly Gaussian distribution with some standard deviation sigma. We know that in reality it cannot be a Gaussian distribution because the density of the distribution at threshold must be 0. However, it's tempting to say, well, it's nearly a Gaussian distribution, and the probability that a trajectory would be at the threshold should be something like the density of the distribution at threshold. So why not write down an escape rate where we say the distribution is a Gaussian and the rate of crossing the threshold is proportional to the density at threshold. So we compare the value at threshold with u0, that's this difference, normalized by the width of the distribution. That would give this density. Now this is only part of the story, because suppose I give a strong current drive. This drive will put the mean trajectory rapidly across the threshold. And in fact, all the other trajectories are driven towards the threshold. So the whole distribution of membrane potentials that we had at time t, this vertical distribution is rapidly pushed across the threshold and gives rise to a distribution of firing times that's also nearly Gaussian. Now, the width of this distribution depends on the slope. This is the slope of the reference trajectory. The more input I give, the steeper the slope, the more likely is that these membrane potential distribution is pushed across the threshold. So we expect that there should be a term that is proportional to the derivative. And this is how we can write this down. And then we have to normalize it in some appropriate fashion. Now this is a heuristic argument. Suppose we simulate a diffusive noise integrated fire model, and we also simulate an integrated fire model with escape noise with this specific escape rate, which depends on the reference trajectory as well as its derivative. And this is what we would find. We give some arbitrary time-dependent input current into the model. First, we simulate it with diffusive noise. The deterministic part of the input gives rise to this deterministic trajectory. Now, for the diffusive noise model, we would have this extra noise term that makes a diffusion of the actual trajectories away from the reference trajectory. And so you may expect that whenever the membrane potential is close to the threshold, the probability of firing is high. Now, if you just repeat this same input stimulus for many times, then you would find this time-dependent interval distribution. The solid line is for the diffusive noise model. But now we can inject the same deterministic current without the noise and add escape noise instead, with an escape rate given by the formula that I indicate with a 4. And if we do this, we find again a time-dependent interval distribution, which can be calculated, and it's the dashed line. And you see that the two interval distributions are nearly the same. Thus, the diffusive noise model, which is nice because it represents stochastic spike arrival, is well approximated by an escape noise model with the appropriate rate. So let us summarize this lecture 6.4. Let me summarize. So we have two different noise models. There's a diffusive noise model, which is nice because it has an easy interpretation in terms of stochastic spike arrival. We can calculate distribution of membrane potentials, and it's easy to simulate on a computer. But it's difficult to calculate something like the interspike interval distribution for arbitrary time-dependent input. The escape noise model, well, for escape noise model, calculating this very same quantity is easy. It does not have the interpretation of stochastic spike arrival. At the start, it's more like an internal noise model. However, as we have seen, with the appropriate choice of escape rate, the escape noise model gives a very good approximation to the diffusive noise model, and therefore indirectly accounts for stochastic spike arrival as well. The advantage of being able to write down interspike interval distribution and hence likelihoods is that we can use this as a basis for neuron model optimization. And that's what we'll do next week. But before we go there, let's have a look at some problems of neural coding.